Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start with the lecture number 4, and the title of this lecture is Microprocessor Architecture. Now, before going to start this lecture, we will review the previous lectures. In previous 2 lectures we did data representation. During that lecture we have discussed about decimal representation, binary representation, 2's complement, hexadecimal representation, and there were like binary addition, binary multiplication, subtraction, addition, and then hexadecimal representation. During that topic we discussed about hexadecimal addition and subtraction and so on. Also we discussed about 2's complement in hexadecimal representation. In the end we discussed about floating point representation, double precision, single precision, and the IEEE standard, how we can represent the floating point numbers. Now we are going to formally start this lecture. This is the outline of this lecture. We will discuss Intel microprocessors initially. During this topic we will go through all the microprocessor lineup from the very beginning to the very latest architectures or microprocessors that have been manufactured by Intel, and then we will discuss about the Intel microprocessor architecture. During this one we will discuss the main components. We will get one general model, microprocessor model. We will discuss what are its registers and other components, how they are interconnected, and then we will discuss in the end about the components of the microprocessor. Just like the registers, there are general purpose registers and special purpose registers. So during these registers we will discuss about the registers which are being used in the earlier computers and the registers which are being used in the new microprocessors. In the end we will discuss about different components of microprocessors, like registers. During these registers we will discuss about general purpose registers and special purpose registers. In registers we will consider the registers that had been used in the previous architectures, in the very earlier architectures, and also the registers that are being used in the new architecture. And we will also discuss what is the purpose of each register, how does it work inside the computer, and so on. So first of all, the Intel microprocessors. In 1971, the very first microprocessor that had been manufactured by Intel, that was the 4004. This microprocessor was used in the BISICOM calculators, and this BISICOM calculator had used this microprocessor, and that was the starting point or the initial step to embed the intelligence in the inanimated object, just like the personal computers and so on. And then after 4004 microprocessor, the Intel has manufactured another microprocessor in 1972. That microprocessor is named as 8008 microprocessor. This was twice as powerful as the 4004. In 1974 there was an article in the Radio Electronics, as you can see at the right side in the picture, that referred a device called Mark 8 that has used this 8008 microprocessor. The Mark 8 is known as one of the first computers for the home, and one that by the today's standards was difficult to build, maintain, and operate. So in this microprocessor, the data word size was 8-bit, clock speed was 800 kilohertz, address space was 16 kilobyte. Instructions, there were total 48 instructions, and register number, like the total number of register, there were 15. And the addressing modes, we will discuss what are these addressing modes. There were register addressing mode. There were three addressing modes. First of all is register addressing mode, or register direct addressing mode, and immediate addressing mode. After that, in 1974, Intel has produced another microprocessor that is titled as 8080 microprocessor. This microprocessor was considered as the brain of the personal computer. The name of this personal computer or the kit was the Altair. So Altair name was chosen from the very famous television show that was called Star Trek. So the base station where this ship they land, its name was Altair, so they used this name. And the Altair kit was sold for like around about $400 each kit, and within months they have sold like thousands, tens of thousands of these kits. This is summary of the 8080 in comparison. You can see 8008 and 8080, the word size, both word size is 8-bit, and the clock speed has been improved in this 8080. It's up to 2 megahertz, and the address space has also been increased, so it can address more around about 64 kilobyte, and the number of instructions are almost similar, like 48 instructions were used, and even the addressing modes are similar in both of these processors. Now in 1978, in 70s, they have produced two microprocessor. They are considered as almost similar, 8086 and 8088 microprocessor. Now 8086 microprocessor or 8088 microprocessor, they became the brains of the IBM's the new hit product that that was the first IBM's product. You can see at the right side, called the IBM PC. The Fortune magazine named this company that business triumphs of the 70s. So this was the very first computer, personal computer, attached with the keyboard, separate keyboard, and so on. So you people can use inside their homes. 286, we mostly know that 286 was invented or produced by Intel in 1982. Actually, Intel 286, or we can call it 286, was the first Intel microprocessor that could run all the softwares written in its predecessors. So whatsoever the previous software that were run on the previous microprocessor, they can run also on this 286. This software compatibility still remains a hallmark of Intel's family of microprocessors. Like still the software that we write for the 286 for like Pentium 1, Pentium 2, they can also run on the backward compatible or the other microprocessors. And within 6 years, this 286 has been estimated like 15 billion 286 based personal computers. They have been installed around the world. So within like 6 years of time frame, there were almost 15 million PCs, 286 based PCs have been sold and installed around the world. And in 1985, they have after 3 years, they have designed a new processor, or invented or launched a new processor that is called the Intel 386T Microprocessor. There were like 275,000 transistors. These are the more than like 100 times more transistor than 4004, and this one is called the 32-bit chip, 32-bit microprocessor. and the main feature that was in the this microprocessor was multitasking. Multitasking means it can run multiple programs or multiple applications at the same time. Now here, after this 286 in 1989, Intel has produced the new microprocessor that is called the Intel486 DX CPU Microprocessor. So Intel 486 was the successor of the 386. So there is one memory of the technology student called the David K. Ellison of the Smithsonian's National Museum of American History, that he said that I could have a color computer for the first time and do desktop publishing at a significant speed. That was his comment about the 486 computer, or the computer equipped with 486 microprocessor. Now, this computer was first to offer a built-in math coprocessor. So this was the first time a separate processor or small processor that was attached alongside with the 486 processor to perform mathematical operation to reduce the burden of the main processor. So they installed the this math coprocessor. So it was used to speed up the computation to off the load from the math complex math functions from the central processing unit, 486 central processing unit, or CPU. Here you can see the list or the comparison of all the microprocessors from 486 and the beyond 486, like up to 4004. Here the main thing you have to observe the increase in the speed. There's an increase in the speed, like from 108 kilohertz to 33 megahertz. And also here you can see the number of transistors. They have increased the number of transistors to make it more efficient, to make the microprocessor more computationally efficient, and so on. Then the addressable memory. We will discuss what is addressable memory. You can see the addressable memory has also been increased. The size of the memory that can be addressed by the microprocessors have been increased. This up to here you can see up to 4 GB of addressable memory is here, and now here is 4 MB. Why? Because this Intel 486SL or single word low power microprocessor. This is the single word external microprocessor that was used for the low cost and low level desktops, and this microprocessor was designed for the notebooks to make it low power. So it was it was going to consume less power than the 486, and this was Intel 486SX was designed for the low cost desktops. Similarly, there are a few terms that we will discuss here. One is the DX and then SX. So there is SX is single word external and DX is the double word. So we discuss single word is 16-bit, double word is 32-bit. So these are the microprocessors for the single word, double word, and this L here represent the low power. So single word low power, single word single word external, and double word external. These are the processor who use the single and the double word for data computation and for their internal registers and so on. Now this is the complete lineup before from 486, before whatsoever the initial microprocessors. Now after that there was another lineup that is called the Intel Pentium processor, then Intel Pentium Pro processors. So Intel Pentium processor allowed the computers to more easily incorporate real world data. This was the first time as I remember, when I used the speech, sound, handwriting and photographic images manipulation inside the Pentium processor in 1994 and 95 when 94 I used this processor. It was first time I recorded sound and could listen voice and all the other manipulate photographic images and so on. In 1995 Intel had produced the Pentium Pro processor. This was the 32-bit architecture and designed to fuel the servers and workstation applications, and it enabled the fast computer-aided design, CAD programs, mechanical engineering and scientific computation. So this was much more powerful than the Intel Pentium processor, and mostly for the scientific and the computationally intensive tasks. They designed this computer for keeping all those tasks in their mind, and they packaged together with a second speed enhancing cache memory chip, and there were like 5.5 million transistors, and it made possible the advanced 3D visualization and interactive capabilities. This is the complete, not complete, but most of the microprocessors lineup that have been produced from Pentium through to the Pentium D processor. You can see in 1997 the clock speed for the Pentium 2 processor was 300 megahertz, and the number of transistors have been increased. So you can see here that this was the one of the fastest processor, like Pentium 2 and Pentium 2 Xeon processor. Xeon was bit powerful than the Pentium 2 processor. After this Pentium 2 processors, Intel has produced another processor family that's called the Pentium 3 processor and Pentium Xeon processor. This Pentium Xeon processor was introduced in 1999. Its internal clock speed was more than the Pentium 2 processor. It was 500 megahertz, and there were like almost 9.5 million number of transistors. So this was the it executed like internet streaming. So you can see it execute internet streaming. There's another key word is called the SIMD, single instruction multiple data extensions. We will not discuss what is SIMD, but this is one of the classification which has been used to classify the microprocessors, the machines, and it extended the concept of processor identification and utilized multiple low power states to conserve power during idle times. This was one of the more famous processor during its time, and after that it's well-known Pentium 4 processor and Intel Xeon processor that was introduced in the market in 2001. Its internal clock speed it was around 1.5 gigahertz, and number of transistors were almost 42 million, and so on. And this was, as we know, that one of the fastest processor in 2001 and 2 and 3 in Pakistan also. So after this Pentium 4, Intel Pentium D processor was introduced in 2005. Its clock speed was 3.5 gigahertz, and 291 million transistors have been used in this microprocessor. So it features the first desktop dual core design with two complete processor cores that each run at the same speed in one physical package. So two processors, same processor in one physical package, and you can install in your desktop or any other machine to run that one. So this is the complete lineup and introduction about the microprocessors that have been manufactured by the. After that one, there are like core Intel Core 2 and Quad Core, Intel Core i3, i7, i5 and i7 and so on. If we will discuss, it will be the discussion will be more intense and it will consume more time. So to keep the time limit in our mind, so we will end this discussion for the introduction here, and we will move towards the main topic that's called the microprocessor architecture. So this is the main point where we will start our subject. I will request to all of you that please focus from here, because architecture is more important to understand, because without understanding the architecture it is really difficult to understand assembly language, because assembly language is second half of the subject. So it's more important to focus here, because without understanding this topic it's not possible to understand the rest of the course. So one thing, if we want to program, if we want to instruct a computer, if we want to write a program, any computer, we want to investigate our instructions on any microprocessor, its internal configuration must be well known. Means whatsoever the internal configuration is, like the memory interfaces, how memory is connected, what are the internal registers, and what is the purpose of each register, and so on. In a multiple core microprocessor, each core contains the same programming model. Means if you understand the working principle of one processor, it means you can understand the working principle of all the cores that have been used in the packaging or in the system. For example, if you don't know the working principle of one microprocessor, and because all the microprocessors are same but they are connected with each other to perform any task, so it is better to understand one microprocessor completely, because all the other microprocessors have the same working principles, and each core runs at separate task or threads simultaneously. So if there are 4 or 5 processors, or maybe 6 processors, 7 processors, whatsoever the number of processors are there, in FPGA there are more than these processors, so each processor runs a separate task or thread simultaneously. So it is better to understand what is being how each task is being executed on one core. So if you understand that one, then it will be easy to understand what other processors are performing in the system. This slide, I've taken the slide from my previous lecture. So this was the very generic, very brief microprocessor architecture. Now in this microprocessor architecture you can see most of the microprocessor components. Like there's a microprocessor here, if my pen is working correctly, so there's a microprocessor here, and there is memory here, and IO subsystem is here. There are input-output devices connected with this IO subsystem, and then there are 3 buses: address bus, data bus, and control bus. So this is very generic, very brief, or very generic microprocessor architecture. We will move in more detail when we will go to the move to the next slide, or next few slides. We will see the details of what is inside these microprocessor. We will discuss about the difference between the old microprocessors and up to the core microprocessors, like the core architectures, quad core and Pentium, and all these architectures like 8-bit, 16-bit, 32-bit, and 64-bit architectures. So here you can see inside the processor, when we magnify, when we zoom in, so we will see there are 3 major components inside the processor. One is called register, second one is called, this is the first component, then we have second component, and then we have third component. So there are 3 main components inside the processor: control unit, arithmetic logic unit, and this registers. Now today we will mainly focus on these registers. What are these registers? Then if you understand the working principle, the functioning function or purpose of these registers, then we will move towards the arithmetic logic unit, and then we will discuss about the data path and control unit in all these systems. There are also address buses, address bus, data bus, and control bus, all the three buses. During the discussion, we will discuss about these buses also. Memory is also the most important part. I will give you a very brief introduction about memory during this lecture, but we will discuss in detail how we can access memory, how a microprocessor can access memory, what are the steps, how we can address each memory location by using these registers or other methods, and so on. So we just move here. This is the very basic the architecture of the 8086 processor. Now you will be more surprised that I skipped all the processor, all the new technologies, and I just used the 8086, the oldest microprocessor. Like I did not discuss Pentium, I did not discuss Pentium 2, 3, 4, and then other processors like Xeon processor and so on, but I just discussed 8086 architecture. You will learn what was the reason behind that one in the next few slides. So here you can see we have some registers here at this point. These are the registers, and here are some registers. There's a control unit, there's a queue. Now this 8 shows 8-bit, 20 shows 20-bit line, and these are the buses. And it's not clear which bus is here, either data or address bus. We'll discuss, but I want to show you the major components in the 8086 architecture. There's also a control unit here, and arithmetic and logic unit, and there's a flag register. Now here you can see the size of these registers is 16-bit. There's AH, AL, BH, BL, CH, CL, DH and DL, SI, DI, BP, SP. And they have got other names also. AX, BX, CX, DX, SI, they have almost up to here, their names are AH and AL is called the AX. This is one register. Then BX, we call BH and BL as the BX, and so on. But these four registers, they have almost similar name, like SI, DI, and BP and SP. There are other registers here. You can see these registers. So what are these registers? But here you can see there is connectivity between all these registers, and from here this line is going somewhere else. So this line connects to the memory or some other devices or input or output device and so on. But here we are selecting by using this. These are called the segment registers: code segment, data segment, extended segment, stack segment, and there is instruction pointer or IP register. Then we have the AX, BX, CX, and DX. These are the general purpose registers. So we call these general purpose. These four registers as general purpose registers. Now AL, from here to here, it is 8-bit register, and this is also 8-bit register. When we combine these two 8-bit registers, we get 16-bit register. Now there are some architectures they use 8-bit registers, and this architecture use 16-bit. This is called the 16-bit architecture. So it combines two registers, or we can call them lower order byte and higher order byte. Actually, this is called the accumulator register. We will discuss what is accumulator register, but here I can give you one short introduction. This accumulator register is a register whatsoever the computation you perform, their results. If we want to perform computation, like if we want to add two numbers, these two numbers may be stored somewhere like in these other registers, or maybe one number is stored in accumulator, one number is stored in another register, or maybe one number is stored in at memory location or somewhere, and one number is stored in the register. If we perform any operation either mathematical or arithmetic or any logical operation, the results will always be stored by the microprocessor inside this accumulator register. Now, this lower order byte are AL and AH. When we combine them in 16-bit architecture, its name will become AX. Similarly, these are called the data registers. So these data registers hold some values, other values, whatsoever value you can assign them. There are source index, destination index, base pointer, and stack pointer register. We will discuss what are these registers and so on in detail. There is arithmetic and logic unit. If we want to perform any operation, how we will perform? We store values somewhere here inside the registers, and or maybe we access the memory or somewhere. We get these values either from memory, either from registers, and send back to the arithmetic and logic unit. This arithmetic and logic unit performs some operations, and the results are sent back to the accumulator, or maybe the results are stored or somewhere else. The results or values are stored somewhere else inside the memory, or we can move some values from one register to another register inside this register file or register area. So this is the path. And also you can see one thing more important here. There is also flag register. Any operation that we perform, for example, if we are going to perform subtraction, or we are going to perform subtraction or addition, whatsoever you can call it. For example, if I want to perform 33 minus 33, what will be the result? Result will be definitely 0. If I want to perform subtraction, or if I want to perform any other operation, whatsoever the results will be, their values will be stored here in the arithmetic and logic unit. However, these flag register will store the status of each operation, each either arithmetic or logical operation. Now there are different flag bits. We will discuss in detail what are these different flag bits. So this flag register shows the status of each operation, what was the result, and either there was result was negative value, positive value, or there was a carry, or there was no carry and overflow, and so on. There was zero result, and so on. So we will discuss all this architecture in more detail, but before that we'll move towards the next slide. And the question is why we chose 8086. As I told you in previously, what was the reason to choose this 8086X microprocessor? 8086 is the first x86 microprocessor. All these microprocessors that you are viewing inside, or you are seeing inside the market, they are called the x86 microprocessor. They belong to this family. So this family starts from here, 8086. So we will investigate the answer for this question, that this is the first processor that belonged to this family, and all the microprocessors from this after this 8086, they are almost backward compatible. If you understand 8086, then 286, 386, there are some extensions in those microprocessors, but there is not something more like, how can we say, dramatic change in these processors, but there are some small extensions in the features, how they have extended the features in 286 and 386 and 486. So there are some extended features in each new model or new microprocessor. So if you understand this 8086 and its architecture, then you can understand easily all the other new microprocessors, but they have some more details that we have, that definitely some of them we will discuss in this course. And the term, as I told you, this term refers, x86 term refers to a family of instruction set architecture, or we call it ISA, or instruction set architecture, based on the Intel 8086 CPU. Now 8086 was launched in 1978 and was fully 16-bit extension of the Intel's early 8-bit. So this was the first 16-bit microprocessor, and also introduced segmentation, like we divide whole memory into different segments to overcome the 16-bit addressing barrier of earlier chips. So here we are using 20-bit addresses. Previously there were only 16-bit addresses and so on. So we cross this barrier of 16 bits. Now we can use 20 bits and more to address the memory. So this was the one major update in the 8086. And then the term x86 and derived from the fact that early successors of 8086, they have also had the names with the ending in 86. So many additions and extensions have been added to the x86 instruction set over the years. Like till now, there are so many instructions they have been added inside this instruction set. What is instruction set? Instruction set is the complete list of instructions and their data sets, their formats that have been directly understood, or that are directly understood by the microprocessor. A microprocessor can directly execute the instructions from this set. So this is a complete set. There are a number of instructions inside this set which are directly understandable by the microprocessor. During assembly language, we will also use instructions from that instruction set. Now, so there are many extensions in this instruction set over the years, almost consistently with full backward compatibility. Now, even though we have extended this instruction set, but still this instruction set is fully backward compatible. Means if you are writing any program for 286, 386, you can execute that program on Pentium machines also. So the architecture, this architecture has been implemented in processors like Intel, Cyrix, AMD, VIA, and many others. x86 processors. Now the processors that belong to this series, or this category, or this x86 family, the first processor was 8086. Now 32-bit family has EP8057, Intel CE, and Atom. 64-bit, this Atom. There are some Atom processors. There's Celeron, there's Pentium dual core, Core i3, i5, and i7, and Xeon processors. Other, we have the Itanium processor, and there are x86 assemblers. We have the A86, A386, FASM, GAS, HLM, MASM, NASM, TASM, WASM, and YASM. So all these are the assemblers that support the x86 architecture. Now that is the reason we have chose the 8086. We could choose 8085, we could choose 8080, we could choose 4004, but we did not choose that one because 8086 is the initial or the starting point of this x86 family of the microprocessors that have been produced by the Intel. Okay, and there are the different number of assemblers. We will choose one of them. Most probably we will use MASM, and maybe we will have introduction about the TASM and so on. This microprocessor, there are 20 address lines. Our address bus has 20 wires. These are called the copper wires or conducting lines to carry out the addresses, to address either the memory, either the devices, either input or output device, and so on. Their names are A0 to A19. There are 20 lines. So the highest memory that we can address is from 0 to 2 raised power 20. So 20 zeros to 20 ones in binary. So this address bus is 20 lines, and we have data bus. Data bus is 16 lines. This is the reason we call them 16-bit processors. So data bus size is 16-bit. So this 16-bit, these lines are 16 lines in data bus, start from the D0 or D0 to D15. D0 is the least significant bit for the data bus, and D15 is the most significant bit. Here is the same is the case for the A0 and A19. So this is the reason we call 16-bit microprocessor, because it has a 16-bit data bus. Here you can see 8086 microprocessor has address bus. This address bus is 20 bits, and data bus is 16 bits, 16-bit data bus. And there are control signals. There are multiple control signals in this microprocessor, we will learn, and these control signals differ for the different architectures and so on. Even the size of this data and address bus differ in the new architectures also, like the Pentium and the Pentium 2, 3, 4 and all these Xeon processors and so on. But here you can see 8086 has address bus. There are 20 lines for address bus and 16 lines for the data bus, and there are some control lines. Address bus is unidirectional. All the addresses go from microprocessor towards the memory or towards the input-output devices. And data bus is bidirectional, and signal or data comes to the microprocessor and leaves from the microprocessor. That is the reason this is bidirectional. 20-bit address bus. Now we will discuss about the 20-bit address bus. Here you can see that A0 to A19 there are 20 bits, so it can be all 20 zeros to, sorry, I'm really sorry about this pen. Still I'm not very much familiar about this pen, how to use this one. So sorry, this you can consider this as a 0. So all these 20 zeros from A0 to A19 are, their values range from either all zeros or all ones. So it can be 20 ones. Okay, I don't know either there are 20, but I can put some dots here so to show that either there are 20 ones from A0 to A19. Okay, now this bus can address any one of the 2 raised power 20 memory locations or addresses. So here you can see this is a representation in hexadecimal. So 4 bits, 4 bits, 4, 4, so and 4 bits. So 4, 4, 8, 8 and 8, 16 and 4, 20. So we need we can represent all those 20 bits by using 5 hexadecimal digits. Okay, hexadecimal digits. So addresses start from either 0, 0, 0, 0, 5 zeros hexadecimal up to F hexadecimal. So 2 raised power 20, I'm sure it's 1 megabyte, 1 MB for 2 raised power 20 memory. Okay, so each memory location is 1 byte wide, is 1 byte wide, or you can say is each location, like here you can see this is first location. Second location will start with the 0, 0, 0, 0, 1 hexadecimal and so on. It will increase like 0, 0, 0, 0 and 2 and so on. It will be again 0, 0, 0 and 9, then A, and all these locations are in hexadecimal and so on. So it will continue up to F. And hold this space from 0, 0, 0 to FF 5F is called the memory address space, the memory space which we can address. So each memory location is 1 byte wide. To store a word, So 1 byte is 8 bit. Now if we want to store a word, for example, and a word is 16 bit, it can be 32 bits if it is double word and so on. So if we want to store a word of 16 bit, then we will have to use 2 memory locations. As you know that integer occupies 2 bytes inside the computer when we use C programming language. So for a word size, it is like double word and quad word or 16 bit or 32 bit, depends what type of operands whatsoever their size is. If you want to store them, they will be stored in this 8 bit or combination of multiple of these 8 bits, like 16 bit word will be stored in these 2 consecutive memory locations. So in what order they will be stored, we will discuss. Either there are 2 terms, we call them little endian and big endian, but we will discuss later on, but that will be the later discussion. But how they are stored or in what format they are stored in 2 bytes, that's another discussion. But for 16 bits and for 32 bits, they will be stored in the 4 locations here. So these 4 bytes, consecutive bytes, they will be used to store 32 bits. Okay, so the first byte of the word at even address 8086 can read the entire word in one operation. For example, I will give you one example. So if you stored your location, your word here, for example, I will write the memory location ... and so on, 0 0 F 0 and 1, this is in hexadecimal, and another location is 0 0 F 0 2 and hexadecimal. Okay, if you store somewhere here, for example, so this is the starting address. Suppose this case differs in either little endian and big endian, we will discuss, but here suppose that this is the starting address of the 16-bit or a word data which we stored in 2 locations. So if we want to access that one, so we will access by using the first address. So the first byte of the word at even addresses 8086 can read the entire word in one operation. So it already know that the second byte also is part of this 16-bit. So the first byte of the word at an odd address, the 8086 will read the first byte with 1 bus operation and the second byte with another bus operation. So it depends, either we are using at even or at odd locations inside the 8086. So how many times we can read this 16-bit, maybe in one go or maybe in 2 goes and so on. There are 2 parts in this architecture. One is called the bus interface unit and second one is called the execution unit. As you saw, we have got in the architecture, we have got the segment registers, then we have got the queue and so on. We got also the control unit, we got the ALU, and here were the general purpose registers, and there were some bus flowing from here, so there was ALU, there were flag registers and so on. So this part is called the execution unit and this part is called the bus interface unit. So upper part is called the bus interface unit and lower part of that architecture that you saw in the previous slide for the 8086 is called the bus interface. Upper part bus interface unit and lower part is called the execution unit. What is bus interface unit? It sends out addresses, fetches instructions, means read instructions from memory, reads data from ports and memory. Ports means either input output ports if we are reading data from input, or maybe we are sending data, reading data from the memory, and write data to ports if we want to send data to the output devices or to the memory. In other words, the bus interface unit handles all transfers of data and addresses on the buses for the execution unit. So all these buses are being controlled by the bus interface unit. Whatsoever the data comes and goes, everything is handled by this bus interface unit. How it is being controlled, that is another discussion. But this interface BIU, or bus interface unit, controls the handles the transfer of data and addresses on the buses. Okay, for the execution unit, because we need data to perform some operations. So all these operations are being executed, are being performed in the execution unit. So execution unit of 8086 tells the bus interface unit where to fetch instructions, data from instructions, or data from decodes instructions, and executes instructions. Now this unit, or the lower part, where we have got all these registers, like general purpose registers, we have got the control unit and so on, we have got the arithmetic and logic unit here, ALU and so on. So this area is responsible to execute instructions to perform some operations, and tells this unit from where to fetch instruction, from where to fetch data and so on, and decode. This section decodes the instruction. I'm really sorry because there is some problem with it. As I told you, there is some problem with this pen. So the lower part, or the execution unit, tells the bus interface unit that from where to fetch data or fetch instructions, and this execution unit decodes. After decoding, it performs execution, or it executes these. So it decodes and executes and tells the bus interface unit to fetch instructions and so on. This is the very brief introduction about these two sections. So, but how we fetch, how we decode, and how CPU perform, or how CPU executes the instruction, that is the part of the subject. So the programming model 8086 through Core 2 or Quad Core, or all the new architecture, they consider the one part. They consider program visible. They have one part is called the program visible, another part is called the program invisible. So this programming model, these registers, when we call programming model, means we are talking about these registers. So 8086 through Core 2 considered program visible section. This program visible section consists the registers that are used during programming and are specified by the instructions. So we use all those registers inside the instructions. There are some other registers that considered to be program invisible. Now this is the another section of programming model, part of the section of the registers. These registers are called the program invisible, means not addressable directly during application programming, means the application program do not address or do not use them directly when that program is being executed. So that section of that part of registers is called the program invisible. Now 80286 and above contain program invisible registers to control and operate in the protected memory and other features of this microprocessor. So, and the 80386 through Core 2 microprocessor contain full 32-bit internal architecture, means the size of these registers is 32-bit. So 80886 through 80286 are fully upward compatible to the 386, 80386 and through Core 2 and so on. That was the reason we chose the 8086, because it is compatible with the all other upward architectures. The programming model of the 8086 through Core 2 microprocessor. We will show in the next slide. It includes 64-bit extensions. 8086 uses 16-bit, 386 and 486 and so on, they use the 32-bit, and there are other new architecture, they use 64-bit architecture. As you have saw that now we have 64-bit operating system to fully utilize 64-bit extensions. So we have seen the general purpose registers, segment register, they were 16-bit, but what are their names when we use them, when we see them, when we visualize them in the 32-bit architecture? So here you can see in the 8-bit architecture, for example, in the 8085 or 8080, this it uses only 8-bit names. So it uses only A, B in the previous architecture, like before 8086. They use 8-bit architecture. They are the 8-bit architecture, so they use 8-bit names, A, B, C, and D, and so on. But here in 8086, it is 16-bit architecture, so they have their names. So there's this AX should be here, so I can write it by using the pen. So 16-bit names are AX, BX, CX, DX. Accumulator is named as AX in 16-bit architecture. B, C, and D, these data registers are general purpose registers. Their names are BX, CX, DX in 16-bit architecture. Base pointer, source index, destination index, and stack pointer. These 4 registers, their 16-bit names are BP, SI, DI, and SP. Now we will move toward the 32-bit architecture, like 386 and upward, up to some other processors. So here you can see their names are only added with EAX, EBX, ECX, EBP, and so on, up to for this 32-bit architecture. Now for this is not 164, but it is only 64-bit architecture. So their 64-bit names are RAX, RBX, only R has been added, replaced with the E. So their main function is almost similar for the EX and EBX, and as accumulator, data register, stack pointer, base pointer, destination index, source index, and so on. So, but their names are different. So if you want to program for 32-bit, for 16-bit, or for 64-bit, you have to use this naming convention. These names will be referred. Okay. So these are the program that is the programming model of 8086 through Core 2 microprocessor, including the 64-bit extensions. Okay, so now here you can see there are some other registers like R6, R9, R10, R11 up to R15, and there is flag register. The flag register name in 80, these are the registers we will discuss in more detail, but before that one, we will discuss about the flag register. This flag register is 16-bit flag register for 8086. This flag register has been extended to its name has been added like E flags for 32-bit and R flags for the 64-bit architecture. Instruction pointer is a register. Its name is IP for 16-bit architecture, EIP for 32-bit, and RIP, and so on. These segment registers, they are same: code segment, data segment, extra segment, and stack segment, and so on. FS and GS are used by the operating system. We are not going to discuss all these registers in detail, but we will discuss the main registers like the flag registers and other registers in more detail, their purpose and for what purpose they are being used. So we will discuss now the multi-purpose or general purpose register. They can be used for different purposes. Okay, the first register, if you want to discuss if you want to know about any processor, if you want to study about any processor, first register that you will study is the accumulator. So accumulator has different names. For 8-bit register it's called A, but for 8-bit is AL and AH. 16-bit is called AX, or it has two 8-bit register like AH and AL. In 8-bit architecture it's only A. There's no AL and AH in 8-bit architecture. But in 16-bit architecture it can be used as a two 8-bit register or a complete 16-bit register. And in 32-bit, as we know that it's EAX and RAX and 64-bit architecture respectively. So this accumulator register is used for instructions such as multiplication, division, and some of the adjustment instructions or the arithmetic logic unit operations. So whatsoever the operation you will perform, this register will store their results. This accumulator will also be part of the instructions where one value is stored in accumulator, another value is stored in another register. We perform addition, subtraction, or other operation between accumulator register or another register. Again, the two values of these two registers will be manipulated, and again result will be stored back to the accumulator. So Intel plans to extend the address bus to 52 bits to address 4 petabytes of memory. They are planning, but here there is RBX and RCX and RDX. So these RBX, RCX, and RDX, these are the three other general purpose registers. These registers are addressable as RBX, EBX, BX, and B register in 64, 32, 16, and 8-bit architecture. BX register or base index sometimes holds offset address of a location in memory system, and all versions of microprocessor sometimes it stores the value of any data or so on. The BX is the base index register, so it stores the memory location in all the versions of the microprocessor. CX stores the is considered as counter or count register, general purpose register that also holds the count for various instructions. DX or RDX is the data we call it data register. So general purpose register holds part of result from multiplication or part of dividend from the division, or also it holds the data. So here we have RBP. RBP is called the base pointer, points to a memory location, base of the memory location. So what is the base of memory location? We will discuss. For memory data transfer, for example, we have a memory location from here to here. So it starts from 000 hexadecimal, and then we have F, all this. So we divide this whole memory into different segments. So for example, this is the starting point of the data segment. We will discuss in more detail. So there is data segment. Now this is the complete data segment. This is a starting point. So this base pointer is being used to now there are other registers. They are called RBP, RDI, and RSI. So RBP or EBP or BP or only B points to a memory location, or is called the base pointer location, base pointer for memory data transfer. So if we want to transfer data to memory or memory to somewhere else, so we will use this base pointer. Then there is RDI. This is called as the destination index register. Often addresses in string destination data, string data type. destination data for the string instructions, the instruction which manipulate strings. Then we have RSI, or source RSI, or source index register. This register addresses source string data from the string instructions, and like RDI, RSI also function as general purpose registers. So RDI, RSI, they also can be used as general purpose registers also. R8, R15, they are found in the Pentium 4 and Core 2 processor. They are not inside the 8086 processor. 64-bit extensions are if we enable 64-bit extension in Core 2 and Pentium, from Pentium 4 to Core 2, they can be used in the these processor, Core 2 and maybe the new processor. So data are addressed as 64, 32, 16 or 8-bit size, and are general purpose registers. So we can use them as a general purpose. Most applications will not use these registers until 64-bit processors are common. Okay, like the 8-bit portion is the rightmost 8-bit only. So we can use 8-bit portion, the right from the 0 to the 7th bit. Bits 8 to 15 are not directly addressable as a byte. So we cannot use them as a separate byte for all these R8 or 15 registers. That was the discussion about the general purpose registers, and now we are going to move towards the special purpose registers. Now we have multiple special purpose registers. They include IP or RIP, SP, and flex and other registers. So instruction pointer or RIP in 64-bit is instruction pointer, stack pointer, and flex. There are other registers. They are called segment register. That they include code segment, data segment, extra segment, and stack segment, and FS and GS. These are also segment register. They are being used by the Windows and other operating systems. Now we will discuss in more detail about these segment register. Now instruction pointer or RIP register or IP register, it addresses the next instruction in a section of memory. Now, for example, we have a whole memory, complete memory. We have the one part of memory. We use this part of memory to store code, and now this whole part of memory is called as a code segment. Now this code segment, there is a in this code segment we want to read instruction from this segment. So we will use this instruction pointer to read instruction from this code segment or the memory area where our program is being is stored. So this instruction pointer will store the address of the instruction that is going to be executed or that is to be executed. So when the instruction is in the execution phase, the next instruction that will be executed, its pointer will be added in the instruction pointer. Then we have the stack pointer. That register is called the SP in 32 bits, SP in 16 bit. For 13 bit is ESP, and then RSP for 64 bit. Addresses an area of memory called the stack. So as we all know that stacks are being stored in a memory, like for example, this is not the memory, this is a stack which I want to show you here. So this is the stack, is the LIFO system, last in first out system. So this is the stack segment, or we can write it here. So another portion of memory we use to store, to implement stack data structure. So in this stack there is a stack pointer which shows the top location inside the stack, or top address where the value will be stored inside the stack. So the stack pointer stores data through this pointer. So this register holds the address where we perform push operation, so it will store at that address and increment, perform some increment. Depends, either we are performing 4-bit or 2-bit storage of 2-bit data or 4-bit data, or 2-byte data or 4-byte data whatsoever. So it will push data and increment accordingly. Similarly, if we want to perform pop operation, then it will decrement and we will read data and so on. So instruction pointer and stack pointer, these are the two registers that will be used to address the next instruction, and the pointer inside the stack where we can store data in the stacks. Now the most important register is called the flag register. So flags register indicates the condition of the microprocessor and control its operation. So this register will indicate the status of the microprocessor operations, and it controls its operation also. Whatsoever the instruction you will execute, it will indicate the status also, and it will be used to control the operation. So flag register of all versions of the microprocessor is shown in the next slide. We will see 8-bit, 16-bit, 32-bit, and so on, all these architectures. And these flags are upward compatible from 8086 or 8088 through new architectures and so on. So there are some extra flags that are being used in the new architectures, but the previous flags are used as it is. They have the same status in the 8086 architecture. The rightmost 5 and the overflow flag are changed by most of arithmetic and logic operations. So we will see what are those flags and how these are being changed by the arithmetic and logic operations. So the data transfers, for example, if we want to transfer data from register to memory or from memory to register, there's no arithmetic and logic unit involved. There's no arithmetic and logic operation in data transfer. So this type of operation will not affect those flags. What are those flags? So for example, here you can see we have different flags for 8086, 8086, 8088, 186, 188. We have the 12 flags, and then for 80286 we have 15 flags from 0 to 14, and then for the 80386 8986 DX double word, and 80486 single word external, Pentium or Pentium 4 up to Pentium 4 where it's shown here. So you can see all these flags. Now we'll see, like up to here you can see here there are 1, 2, 3 and 4 flags. As we already discussed, that flags never change. Never change for any data transfer or program control operations. Like if we want to jump to another instruction and the location inside the program, or we transfer data, it doesn't affect the flags. Some of the flags from here, few of the flags are also used for the control features found in the microprocessor. Now just keep in mind there is C, P, A, Z. So these are the very common, we will not discuss all of them right now here. These are the very common operations or status register flags that we already know inside the arithmetic of the binary arithmetic and so on. What are those flags and what is their purpose? C shows the carry. Now these flag bits, one of them, like the lower order byte, lower order first byte bit of this carry, this flag register is called carry. This carry holds after addition or borrow from subtraction. So this, if it is 1, means there is a carry has been there was a carry inside the arithmetic operation. Or if we borrow in subtraction, so this bit will be 1. Now if there was no carry involved, then there will be this bit will be 0. Now in there is P or parity flag. This bit in the flag register is the count of ones in a number expressed as either even or odd. So parity can be either even parity or odd parity. So if this parity bit is 0, then it means odd parity. Odd parity means the number of ones are odd. So logic 1 or this parity bit will be 1 or set or high for even parity. So if a number contains 3 binary 1 bits, for example, if we have a number or we perform operation and the result is 0, 1, 1, 1, 0, 0 and 0, for example, this is the result. So it's called the odd parity. So for odd parity, this will be this bit will be 0, and like for this one odd parity. And even for even parity, if a number contains no 1 bits or even bits, or it has even parity, for example the even number of ones, so this will be 1. So after that, carry and this parity flag, there is auxiliary carry E. This auxiliary carry holds the carry if there was a carry in the operation addition or borrow in the subtraction in the half of the results. I will show you. I will draw this one here. Still, okay. So there is another flag bit is called the auxiliary carry. This auxiliary carry holds the carry or half carry after addition or borrow after subtraction between bit position 3 and 4 of the results. Like for example, if we perform addition or subtraction for 8 bits, so if there is carry or borrow between bit 3 and 4, if we perform addition of 2 bits or 2 numbers, so this bit number is 4, and 3. So if there is any borrow from or carry from 4 to 3, so this bit will be flag will be high to show that either there was borrow or either there was a carry from 3 to 4 or borrow from 4 to 3 and so on. So and there is 0 flag. Here you can see we have 0 flag. This 0 flag shows that the result of an arithmetic or logical operation is 0. For example, if we add 2 numbers, if we perform AND operation or operation exclusive, or if we perform any other operation, either arithmetic or logic operation, if the result is 0, this 0 flag will be high. If result is either negative or positive, it doesn't matter. It will be 0. The 0 flag will not be 0, but its value will be 0. And another flag bit is called the sign flag. So sign bit or sign flag bit holds the arithmetic sign of the result after an arithmetic or logic instruction executes. For example, if we execute an instruction, an operation, or if we perform an operation, or if we execute an instruction which perform either arithmetic or logical operation, and if the result is negative, it will be 1. If result is positive, it will be 0. There is another one flag is called trap flag. The trap flag enables trapping through on-chip debugging features. This is not part of this one, so we can just skip this one. Interrupt or I flag controls the operation of INTR interrupt request pin input pin. Now when we will perform interrupts by using the inside the assembly language, we will discuss about these interrupts. So there are interrupt requests. There are some priorities of those interrupts, but this flag controls the operations of the interrupt request pin in. This is the input pin to the microprocessor. And this direction flag bit selects the increment or decrement mode of the DI, destination index, and our source index registers. So what is the direction? Either in the positive direction or the negative direction, we are in increment or decrementing the segments. So the next one is called the overflow flag. This overflow flag occurs when signed numbers are added or subtracted, as we discussed in the addition and subtraction of the binary numbers. So this overflow bit indicates either there was overflow or not. In case of overflow, it will be 1. In case of no overflow, it will be 0. And overflow indicates the result has exceeded the capacity of the machine. For example, if we have 16 bits, 16-bit architecture 0 to 15, and if we are performing addition or subtraction, and if it exceeds the 16-bit size, so it will indicate either there was overflow or not. Okay, so this was the introduction about few of the registers. Now there are segment registers. So these segment registers generate memory addresses when combined with other registers in the microprocessor, like code segment, data segment, stack segment, extra segment, and so on. So these segment registers are used to address memory in combination with the indexes. We will see here 4 or 6 segment registers in various versions of the microprocessor. There are 4 or 6 segment registers. These 4 are very common in all the architectures, like the as I told, data segment, stack segment, extra segment, and code segment. These are the 4 common segment registers. A segment register functions differently in real mode than in protected mode. So we will discuss what is real mode and what is protected mode. We will discuss how these registers work in the what is the purpose of each of these registers. Now CS is the code segment register. This code segment register holds the code. So there is one area inside the memory, as I've drawn in the previous slide, that if we start memory from 000 hexadecimal and so on. So we have 00 F, and so on hexadecimal. So one area where our code is being stored, we call them that area as a code segment. So the programs and procedures are stored in this area. So this register, segment register, holds the code used by the microprocessor. So this code segment register will store the address or starting address of this segment register code segment. Similarly, we will use some indexes alongside with this segment register. So to access this segment area, code segment area. Similarly, there is data segment register. It contains most of the data used by the program. So data are accessed by an offset address or contents of other registers that hold the offset address and so on. So we will use this register if we want to access the area where our data is being stored. So that area is called the data segment. Similarly, is called the extra segment. Extra segment, an additional data segment used by some instructions to hold destination data and so on. We will use to store temporary data inside the extra segment. And then there is a stack segment. We know that stack segment is a segment or a portion inside the memory where we store data, define the area of the memory used for the stack. So stack entry point is determined by the stack segment. So this is the stack entry point. This is determined by this stack segment and stack point register. So stack segment and stack point register, they are used in combination, as I told you, that the code segment, data segment, and the extra segment, they are being used with some pointer registers to access the data or any point or any address inside those segments. And the base pointer register also addresses the data within the stack segment. So there is a BP, or base pointer register, is also used. So FS and GS, these are the two segment registers. They are not used in the 8088 and 8086. They are available in 80386 up to the new architectures, new microprocessor. And these two segment registers allow two additional memory segments for access by the program, that is being accessed by the programs. Usually these operating systems use this segment. So Windows uses these segments for internal operations, but not definition of their usage is available. So now we are going to summarize. In this lecture we discuss the brief history of the microprocessors, and we also discuss the general microprocessor architecture, like the 8086 microprocessor. And inside this 8086 microprocessors, we discuss about the bus interface unit and the execution unit, and so on. There are two main sections. There are some registers and so on. We also discuss about the registers, general purpose registers, segment registers, and flag registers. So general purpose registers are, we can call them multipurpose register and so on. So accumulator and other registers, AX, BX, CX, and so on, DX. There are in 64-bit architecture, they are being called RAX, RBX, RCX, and etc. There are segment registers and there are flag registers. Now there is also one flag register. So this flag register indicates the results, or whatsoever the operation that we perform, flag register indicates the operation result. So this is end of this lecture. Hope to see you in the next lecture. Till then, Allah Hafiz.